Hello everyone, my name is Divyam Goyal. I'm an undergrad at UC Berkeley and I'm assisting in research at the Space Sciences Laboratory, where we are trying to explore the effects of geomagnetic storms in the ionosphere and specifically the thermosphere using data from NASA's Gold mission. The instrument is in a geostationary orbit positioned above the South Atlantic anomaly. This orbit produces a geospatial temporal dataset that provides a consistent view of one part of the Earth at different times. Such characteristics of the data allow us to compare storm time conditions with quiet time conditions. We specifically look at the O into column density ratio as a parameter to study the compositional perturbation of the thermosphere during geomagnetic storms. We decided to employ principal component analysis to quantify the major modes of variability without any human bias. Principal component analysis is an unsupervised learning algorithm that reduces the dimensionality of the data while retaining its trends and patterns. In our study, the algorithm is trained to identify the major modes of variation, of spatial variation in the O into column density ratio for April of 2020. The basis vector, the basis of the eigenvectors in our PCA are locations, and the scalar factor is the O(n)2 ratio. The first principal component shows meridional variation, while the second principal component shows longitudinal variation, and the third principal component shows a mix of longitudinal and latitudinal variation in the O(n)2. These three components together explain 37.2% of the variance in the month. To understand the effects of the geomagnetic storm that happened on day 111 of 2020, we conducted PCA on a dataset which had data from all the days of April 2020, and we conducted PCA on a dataset which had data removed from days 111 and 112 of 2020. We observed that the plots for the first principal component showed a significant amount of difference, which meant that the geomagnetic storm contributed to a significant amount of variation in the month of April, while the second and third principal components stayed relatively the same. This is because the second and third principal components are influenced by local time variation, and the storm is concentrated at very high latitudes. So there's not much effect on the local time variations in the data we are looking at from the storm. The results from this comparison of the first PC motivated us to then explore how the weights of each principal component were changing over the entire month. We subtracted the O(n)2 observations of April of each location by the mean of the O(n)2 value at each location. We then took the dot product of the result with the eigenvectors of each PC to compute the weightings of each PC. The weights of the first principal component showed that the storm day had the greatest influence on the first PC, while the other principal components were relatively the same. However, we also noticed that the weights of the third principal component showed a 6-day periodicity. So to check our observations in the real data, we averaged all the data between latitudes 50 and 60 and longitudes -70 and -40 for each day of the month. We then observed that the average for each day also had a 6-day periodicity. This makes us suspect that there's a quasi 6-day wave that is modulating the O(n)2 in the atmosphere. Thank you.